Welcome back to Computer Lessons.
Imagine taking a physical letter, cutting it into 1,000 tiny confetti pieces, and throwing them into the wind. Now imagine that wind carries those pieces across the ocean, through hurricanes and storms, and they miraculously reassemble themselves in the correct order on your friend's desk. This sounds impossible in the physical world, but this is exactly how the internet works every single millisecond. The internet does not send files as solid blocks of data because a single error would require resending the entire file. Instead, it uses a technology called packet switching. Whether you are sending an email or streaming a 4K movie, your computer chops that data into tiny, manageable chunks called packets. Each packet is like a digital envelope containing a small piece of the puzzle. Just like a real envelope, it has a header containing metadata about where it came from and where it is going. Inside is the payload, the actual slice of the photo or text message you are sending. Finally, there is the trailer, or footer, which acts as a security seal. It contains error-checking data to ensure the payload wasn't corrupted or altered during its journey through the wires. But for this envelope to be delivered, it needs a unique address. Enter the Internet Protocol address, or IP address. This is the fundamental coordinate system of the digital world. Without an IP address, you do not exist on the network. You are a ghost without a location. For decades, the world has run on version 4 of this protocol, known as IPv4. An IPv4 address is a 32-bit number, usually written as 4 numbers separated by dots, like 192.168.1.1. The math behind this is simple. 2 to the power of 32 gives us roughly 4.3 billion unique combinations. When the internet was invented, 4.3 billion seemed like an infinite number, enough for every computer that would ever exist. The engineers were wrong. With the explosion of smartphones, smart fridges, and watches, we technically ran out of these addresses years ago. To solve this crisis, engineers created the ultimate successor, IPv6. Instead of 32 bits, IPv6 uses 128 bits, written in a complex hexadecimal format with colons. The number of available addresses is not just double, it is exponentially larger. To visualize the scale, if IPv4 was the size of a golf ball, IPv6 would be the size of the sun. We could assign an IPv6 address to every single grain of sand on Earth and still have enough left over to address other planets. It effectively future-proofs the internet for eternity. But if we ran out of IPv4 addresses years ago, why is the old system still working today? The answer is a clever trick called NAT, or Network Address Translation. This is the most important job of your home router. Think of your home network like an apartment building. The building has one main address on the street. This is your public IP, assigned by your service provider. But inside the building, each apartment has a private number, like apartment 101 or 102. Your router acts as the doorman. When your phone sends a request to Google, the router intercepts the packet, erases your private apartment address, and stamps its own public IP on the envelope. To the outside world, every device in your house looks like one single computer. When Google sends the reply back, the router remembers which device asked for it. It looks at its translation table, restamps the packet with your private internal address, and forwards it to your phone. This trick allowed us to connect billions of devices using only a few million public addresses. But how does your phone get that private address in the first place? You don't type it in manually. This is handled by a protocol called DHCP, or Dynamic Host Configuration Protocol. When you walk into a coffee shop and connect to Wi-Fi, your phone shouts, "Hello, I am new here. I need an identity." The DHCP server hears this and leases you an available IP address from a pool. It is a temporary rental. When you leave, that number is recycled for the next customer. We must also talk about the subnet mask. usually seen as 255.255.255.0. This number tells the computer which part of the IP address represents the neighborhood and which part represents the house. It defines the boundaries of the local network. Once a packet leaves your local network, it enters the wild west of the internet. It passes through dozens of routers, which are the traffic cops of the web. Each router looks at the destination IP and decides the fastest path to the next hop. Interestingly, packets from the same file might take different routes. Packet A might travel through Paris, while Packet B travels through London. They arrive out of order, and it is the receiving computer's job to reassemble them correctly. To prevent lost packets from wandering the internet forever, we use a failsafe called TTL, or Time to Live. This is a number stamped on the packet header that counts down by 1 every time it passes through a router. If the number hits 0, the packet is killed. This destruction prevents zombie packets from clogging up the global infrastructure in an infinite loop. But what happens when a packet is lost or killed? That depends on the transport protocol, TCP or UDP. TCP, the Transmission Control Protocol, is the reliable perfectionist. When it sends a packet, it waits for a confirmation receipt from the receiver. If it doesn't get a receipt, it resends the packet. This ensures 100% accuracy, which is vital for emails and websites. You wouldn't want an email to arrive with missing letters. However, this constant back-and-forth conversation creates a slight delay. UDP, the User Datagram Protocol, is the speed demon. It fires packets as fast as possible without caring if they arrive. It is used for streaming video and online gaming, where speed is more important than perfection. If you drop a few packets in a video call, the image glitches for a split second, but the conversation continues. If we used TCP for a live call, the video would freeze constantly while waiting to recover a single lost pixel. It is a trade-off between reliability and velocity. Finally, we have the concept of ports. If the IP address is the building, the port is the specific door you want to enter. Web traffic usually enters through port 80, while email enters through port 25. This allows your computer to do multiple things at once. It can receive email packets and Netflix packets simultaneously because they are knocking on different doors. The operating system knows exactly which application to send the data to. There is one IP address that is special, 127.0.0.1. This is known as localhost. It is a loopback address that points directly back to yourself, used constantly by developers to test software without leaving the machine. Understanding IP addressing is like understanding the postal service of the digital age. It is a system of logic that turns chaos into order. But memorizing these numbers, 192.168.1.1, is impossible for humans. We prefer names, not numbers. We want to type google.com, not a string of digits. In the next video, we will explore DNS, the phone book of the internet, which translates human language into machine coordinates.
Tell me in the comments, have you ever had to manually configure a static IP address to get a game or a printer to work? If you found this explanation helpful, please hit the like button and subscribe to Computer Lessons. Don't forget to click the bell icon so you don't miss our next class. Thanks for watching, and keep learning.